Our presentation is on enhancing mathematical reasoning in LLMs. So, as we all know, large language models are getting increasingly powerful at complex tasks. However, LLMs have consistently shown poor performance on tasks requiring mathematical reasoning. Intuitively, the underlying mathematical reasoning in evaluating arithmetic problems is the same as that in tasks like math word problems and code generation. So, if an LLM can be trained to develop mathematical reasoning, it will directly translate to many tasks such as math word problems and code generation. The ultimate goal is to develop an LLM architecture, which we call AIR2, achieving enhanced mathematical reasoning. Our main task for this project is to investigate the hypothesis that pre-training on arithmetic problems translates to improvements on math word problems. And the question that we investigate is what strategies work best for developing this understanding. Some related work. So, pre-trained language models such as MathBERT and GenBERT demonstrate enhanced capabilities for numerical reasoning by incorporating mathematical data and formulas in their pre-training. Instruction learning models such as MathGLM and GOAT enhance LLM's performance by incorporating that in fine-tuning. And finally, tool-based methods involve models such as Symbol LLM and PAL, integrate mathematical tools like symbolic solver and calculators to enhance their mathematical performance.
So the datasets used in this project include both arithmetic datasets and math word problem datasets. The arithmetic dataset was a novel contribution because there was a lack of openly available arithmetic datasets that provided intermediate evaluation steps. So if you look on the right, you can see the original arithmetic expression as well as the intermediate steps to actually evaluate that to get to the result. There's also other factors that are important that we use in chain of thought prompting. And it's also very tunable. You can tune it according to like the number of samples you want, the difficulty of the expressions, etc. We also use math word problem datasets, including ASDIV, math, and GSM8K. So now, going into our methods, our pipeline basically consists of taking a model, pre-training on arithmetic, either on the simple or hard data set, and evaluating this on arithmetic and math word problems and comparing it to the baseline. You can also fine-tune this after it's been pre-trained on arithmetic, fine-tune it on the math word problems, and compare that to a baseline that has been fine-tuned on math word problems. And by comparing these, we can see if transferability is actually occurring. And we use a multitude of strategies including LoRa and full for training, as well as prompting strategies such as few shot prompting, chain of thought prompting, expression within a sentence, mixed training, etc.
On this slide, we see the evaluation results before the fine-tuning. On the first table, we see a comparison between the baseline model, which is DeepSeek, and the pre-trained model on arithmetic on two different tasks, arithmetic and MWP. We see that in arithmetic, the performance has improved significantly, and on MWP, we see a slight improvement. For the second table, we also used other prompting strategies such as EWS, COT, and using a mixed arithmetic and MWP dataset. The performance is slightly worse, but the same conclusion follows. For this second slide, we see the evaluation after the fine-tuning. So after the pre-training on a arithmetic dataset, we fine-tuned on the MWP datasets. We see that the model still retained its ability to do arithmetic and improved its performance on MWP. And this supports our conclusion of the transfer learning.
Yeah, so when diving a bit more deep into our arithmetic performance, we analyzed that pre-trained models generally outperform the baseline DeepSeek model in simpler arithmetic tasks, but they struggle more with complex arithmetic problems. But within the set of complex arithmetic problems, we observed that pre-trained models consistently outperform the baseline model anyways. And then when we were analyzing our MWP performance, we saw that errors in responses from the language model often stem from the miscalculations at specific steps or failures in logical reasoning through the problem solving steps. In addition to this, fine tuned models showed improved capabilities in solving MWPs by demonstrating better mathematical reasoning. So, our conclusion is that our results suggest that arithmetic pre training can enhance mathematical reasoning for language models. However, the results for solving arithmetic and MWPs are not perfect. And reasons for why include using a very small model and using a model that was pre trained on code. So, some future work consists of training math models, such as DeepSeek Math 7 billion Instruct, and then developing AIR2, which we mentioned earlier, is a custom parameter efficient memory module to enhance an LLM's mathematical reasoning capabilities, and then also evaluate AIR2 to confirm its mathematical tasks relative to LLM models. Thank you.